This is a tutorial presentation designed to help us understand the relationship between atomic orbitals, the structures that we've just finished looking at, and bond formation. Well, let's start out with a very simple system, just two hydrogen atoms in space. Here we see that awful solar system representation where we have a nucleus with a single proton and an electron in a solar system orbital around that nucleus. What happens as these two atoms start to approach each other? Well, as they become closer, what happens is the electrons in one of the atoms starts to be attracted towards the positive nucleus in the other atom. Since opposite charges attract, there's a force that is bringing these atoms together. And we end up with a system that has more stability and lower energy. Well, what happens if we continue to close the distance? As those atoms become closer and closer, we end up with a situation where the like charges start to repel each other. That's repulsion of the two electrons for each other and repulsion of the two nuclei for each other. And we end up with a system that is becoming more unstable and a higher energy. Since energy is the reason for everything, it's these considerations that are going to govern whether or not we form a bond. If we can find a distance that maximizes the attraction of the opposite charges for each other while minimizing the repulsion of like charges, the atoms will stabilize that distance and form a bond. Well, let's see how that bond formation overlaps with our understanding of quantum theory and how we're going to form that chemical bond. From an energy point of view, what happens as these atoms approach each other? Well, we're going to draw a diagram that has distance on the x-axis and energy of the system that we're looking at on the y-axis. We're going to designate zero energy when those atoms are so far apart they have no interaction. We will look at negative energy and positive energy of this system of two hydrogen atoms as they approach each other. So we're going to start out with those hydrogen atoms at infinite distance. They have no interaction and therefore zero energy when we're considering those two atoms associated with each other. If, as those hydrogen atoms become closer, we can overlap our atomic orbitals, and as a result of that, the system energy is lowered, then a molecular bond will form. So let's take a look at the representations we've got here. We've got those two hydrogen atoms with electron clouds. As those electron clouds overlap, the electron clouds become distorted as those electrons are attracted not only to their own nuclei, but the nuclei of the neighboring hydrogen atoms. If this results in a decrease of energy, a decrease in the system energy, where the definition of our system is two hydrogen atoms, then we have a situation where the system becomes more stable, less reactive. That difference in energy is what we would refer to as an exothermic process, and that energy decrease in the system forces the energy out into the surroundings away from the system. As the system energy decreases, it has to give up that excess energy, and that energy moves to surroundings. You'll notice that there's a certain distance at which we reach an energy minimum, and as we continue to try to force those atoms closer together, the energy of the system climbs as that repulsion between like charges starts to have a greater and greater influence. If we consider a system where there's no decrease in energy, well, let's consider two helium atoms approaching each other. We see no energy minimum, just increasing repulsion as those two atoms come together. The result is no bond formation. As I insist with almost every topic that we have, energy is the reason for anything. And if you can figure out how energy changes during the course of the reaction that we're taking a look at, then we can rationalize why we end up getting chemical bonds. Linus Pauling, who is one of our graduates, earned the Nobel Prize in chemistry. We have the Linus Pauling Science Center, where part of the chemistry department is located, was the first person to really apply quantum mechanical principles to the formation of molecular bonds. Well, let's take a look at how the overlap of atomic orbitals will end up giving us stabilization and forming molecular orbitals. Let's consider the overlap now not of s orbitals, but of p orbitals. P orbitals classically are drawn as some sort of dumbbell shape, where we have a probability of finding electrons on either side of the nucleus. Well, what happens if we get head-to-head overlaps of those dumbbells? Well, we start out with two half-filled p orbitals. When we get head-to-head overlap, those electrons pair up. They are physically located now not on either side of the nucleus, but physically located between the two nuclei. So each individual electron is not only attracted to its own nucleus, but the nucleus of the atom that it's attracted to, forming a bond. We end up then with one molecular sigma orbital. So that little symbol that we see there is a Greek sigma. So we end up with one molecular sigma bond that results from the head-to-head overlap of these p orbitals. Well, the p orbitals show up in all of the Cartesian coordinates. What happens if we end up with two p orbitals that are not aligned head to head, but are aligned side to side? Again, we have electrons, one electron in each of those p orbitals. As they combine to give us one molecular orbital, we have now not head to head overlap, but side to side overlap. And when we have this side-to-side overlap, we will form a pi bond between those two atoms that are coming together to form a molecular orbital. So we will first get one molecular sigma bond where we have the electrons located geometrically between the two nuclei. And then secondarily, we can form a second bond, a pi bond, where we have our electrons both above and below the location of our nuclei. Quantum orbital calculations show that there's less overlap in a pi bond. What should that mean about energy? Well, if we have less overlap of the atomic orbitals, we would expect there to be less energy holding those atoms together. Well, in fact, if we go ahead and measure the energy of first a carbon-carbon single bond, then a carbon-carbon double bond, which is one sigma bond and one pi bond, or a carbon-carbon triple bond, one sigma bond, two pi bonds, we see an energy distribution that looks like this. Of course, as we share more electrons, the stability, the energy of those bonds goes up. We go from sharing 2 electrons to sharing 4 electrons to sharing 6 electrons. Each of those sharings then brings those atoms closer together, results in a stronger bond. But if we go ahead and calculate the energy of the individual bonds we're adding, we find that a carbon-carbon sigma bond on average has about 347 kilojoules per mole of sigma bonds created. If we take a look then at the energy of the pi bond that's formed secondarily, we see that pi bond, because it has less overlap, has less energy holding those atoms together, 264 kilojoules per mole. And then finally, as we add that second pi bond, our second side-to-side overlap for those p orbitals, we end up with less energy associated with that second pi bond. So if we add up the total energies, it continues to go up as we share more electrons. But we can see individually we have a better overlap head-to-head in our sigma bond. Not as much overlap, so less energy in that first pi bond. And then finally, less energy of overlap in that second pi bond. Well, let's take a look at how valence bond theory then predicts those those orbital overlaps, and how we're going to transition from the concept of atomic orbitals, sp, d, and f orbitals, into the more complex situation where we're creating molecular orbitals. So the question we're asking is, how will we use this concept of atomic orbitals to form the more complex molecular geometries that we've already talked about? Well, most often we'll do this by taking our atomic orbitals and combining them or averaging them both in energy and geometrically in space to form our molecular orbitals. Well, here are the rules for our molecular bond formation. Is we're going to try to maximize the atomic orbital overlap during bonding, because that will give us a bigger overlap and a stronger bond. Simultaneously, we will try to minimize the electron pair repulsion, which is fighting bond formation, and we'll do that by trying to optimize the geometry in three-dimensional space the way that we've already looked at. If we can do that, this will result in stronger, more stable, less reactive chemical bonds. And the universe is always trying to push systems towards more stability, lower energy, less reactive molecules. Again, energy is the reason for everything that we look at. Well, we're going to now introduce the concept of hybrid orbitals. Well, when we took a look at the atomic orbitals for carbon, the first thing that we did was we looked at 2s and 2p orbitals. The s orbital we said was spherical, centered around the nucleus. We've got 2 electrons in that 2s orbital. And then we said that we had 3p orbitals that were in the XYZ Cartesian coordinates. We then went ahead and filled in this idea of electron probability or electron clouds that looked like these dumbbells distributed around around both sides of the XYZ coordinates. And we said that we had 2 electrons up in those 2p orbitals. Well, and a 90-degree separation between those orbitals. Well, what we're going to do is we're going to take those concept of atomic orbitals, and we're going to form what are referred to as hybridized orbitals or hybrid orbitals that attempt to maximize the atomic orbital overlap during bonding, because that bigger overlap is going to give us stronger bonds, by minimizing the electron pair repulsion. Well, electron pair repulsion, we already decided was going to determine molecular shape. Well, taking a look at the atomic orbitals we have in our current diagram, is 90 degrees away from each other the best that we can do for those p orbitals? And of course, the answer is no. If we combine our one s orbital, it's a 2s orbital, but we only have one of them, with our 3p orbitals in that designation, if we combine those into 4 equal energy hybrid orbitals, what we find is those 4 hybrid orbitals, 4 repelling groups of electrons, end up giving us a tetrahedral structure, as opposed to a spherical structure for the s orbital, and then the 90-degree structure for those p orbitals. We end up with 4 equal energy orbitals that, from an energy point of view, are the average between the s orbital and the 3p orbitals. And we now end up with electron clouds that are 109 degrees apart from each other. As far as the carbon atom is concerned, carbon will be contributing 1 electron into each of those now sp3 hybrid orbitals. And those orbitals, as we know from our structures that we've already taken a look at, those orbitals will be separated by 109.5 degrees in space. That's a perfect tetrahedron. And then our hydrogen atoms will come in, each contributing a single electron, giving us that octet, complete octet as far as carbon is concerned, that we're pursuing. Now, you'll notice that although our p orbitals started out as a symmetric dumbbell shape, that in fact, once we form our atomic or our molecular orbitals, that almost the entire electron probability is towards the atom that we're binding with. And although we do maintain two lobes, one on either side of the carbon nucleus, the probability of where we're going to find our electrons is almost universally between the carbon nucleus and the hydrogen nucleus. All right, what would we expect to be different for ammonia, NH3? Well, we're going to hybridize our four orbitals into sp3 hybrid orbitals. Nitrogen, because it has a lone pair in one of those sp3 orbitals, will have its own electrons. And then as we add in the atomic contributions for the hydrogen atoms, we see that the rest of those sp3 hybrid orbitals fill out. For water, we're going to expect the same thing in those sp3 hybrid orbitals, and then the hydrogens come in and fill out the octet. Well, let's see how that corresponds to molecular geometry and all of the mental gymnastics that we played with as we were combining orbitals to give us our molecular shapes. All right, so the question is, what's the molecular geometry that we expect? How many electron repelling pairs is that? And how do we expect that to interact with our understanding of atomic orbitals transitioning now into molecular orbitals? All right, so when we have a linear molecule, we've got two repelling electron pairs, and the way that we get from two electrons in an s orbital, atomic orbital, to two electrons in bonding orbitals, if we need to have two unpaired electrons so that we can bond using those electrons, we're going to pull one of the p orbitals down to the s orbital and hybridize in an sp hybridization. That gives us our two electrons in individual orbitals, unpaired. Those two electrons now can pair up with available electrons with two other atoms, giving us sp hybridization, where we have paired up the two available electrons. So if we see a geometry that's linear, because we have two pairs of repelling electrons, our hybridization is sp. We have hybridized the s orbital with one of the p orbitals, and then used those unpaired electrons to form two molecular bonds. Well, what happens if we have a molecular geometry that's trigonal planar? Well, we arrived at trigonal planar because there were three repelling electron groups. Well, for atomic orbitals, that would mean we would have two electrons in the s orbital, one electron in the p orbital. But as soon as we need to use those electrons to form molecular bonds, we end up with sp2 hybridizations. We've got three electrons. We want to split those three electrons into individual orbitals of equal energy so that they can be used to form molecular bonds. Well, sp2 hybridization means that we've started out with an s orbital and two of the p orbitals because we have three electrons. We're going to form three orbitals of equivalent geometry and equivalent energy, that's sp2, so that I can then go in and share those three electrons with three electrons from other atoms to give me three bonds. Well, that's sp2 hybridization, three repelling electron pairs, trigonal planar. Well, now we're finally at the carbon example, where I've got four repelling pairs of electrons. That means that from the atomic orbital point of view, here towards the top of the screen, I started out with a carbon atom with two electrons paired in the s orbital and two electrons split into individual p orbitals. What I need to do is I need to split those four electrons up into equivalent orbitals, both from a geometric and an energy point of view, so that I can distribute those four electrons into those newly created molecular orbitals, and then pair those up with four other elements that are sharing a single electron piece. So if I have a tetrahedral configuration, that means I had four repelling electron pairs. That means that I had to hybridize my orbitals into sp3. I combined one s orbital with three p orbitals to give myself sp3 hybridization, which gives me that tetrahedral electron geometry. How about trigonal bipyramid? Well, I've got five repelling electron pairs. If I go ahead and look at my atomic configuration, that's two electrons in the s orbital and three electrons in the p orbitals. But I need to create five orbitals that I can form molecular bonds with. Well, that means it's if I need five orbitals, that's an s orbital, that's three p orbitals, and a d orbital. I now have sp3 dehybridization. That's five orbitals. My five electrons from my original atom are distributed in those five orbitals, unpaired. And now I can bring in five other atoms to share individual electrons in those five orbitals. If I have five repelling pairs of electrons, that gives me sp3 hybridization. sp3 hybridization is a trigonal bipyramid. And of course, we're going to finish off with octahedral. If I take a look at six repelling pairs of electrons, well, if I go back to my atomic orbitals, six electrons is two in the s and four in the p. Four in the p means I was forced to pair up a couple of those p electrons, but I still have two unpaired p electrons. Well, that means if I need to take those six electrons and distribute them into six separate orbitals, that's one s orbital, three p orbitals, and two d orbitals. My hybridization now is sp3 d2. I'm going to distribute my six electrons that my central atom started out with into those six separate orbitals unpaired. And then I can go ahead and bring in an additional six electrons from other atoms, completely pairing up the six electrons that I started out with my central atom. What would we expect for the energy levels of these hybrid orbitals? Well, they should have an identical energy. With the exception of the trigonal bipyramid, which is a molecule which does not have symmetry. We've got those three positions in the triangle that we know are lower repulsion than the two the two positions at the apexes of that bipyramid. So there will be a slight energy splitting there. All right, finally, let's finish off talking about the concept of hybrid orbitals and how we form double bonds. Well, what's the difference between electron geometry and molecular geometry? Well, it's the difference between repelling electron pairs and non-bonding electron pairs. Well, let's take a look for a minute at the analysis of how many electron pairs we have and what type of geometry we end up with. Well, let's start out with a geometry that's trigonal planar and see how that affects the formation of single bonds, sigma bonds, and pi bonds in our molecules. All right, so trigonal planar is three repelling electron pairs. Three repelling electron pairs means that our hybridization, no matter what molecule it is, has to be sp2. All right, let's start out with a simple molecule like aluminum trichloride. Aluminum starts out with three electrons. Aluminum is group 3. That means three valence electrons. If I'm going to use all three of those electrons to form bonds, they need to be in separate orbitals. The way I'm going to do that is by hybridizing an s orbital and two of my p orbitals to give me sp2 hybridization. And the molecule then is going to be trigonal planar, looks like this, where I've got, so remember the the definitions of how we're using these images. When I have that triangle that's colored in, that chlorine and its bond are projecting out of the screen. When I have that crosshatch to the other chlorine, that chlorine is projecting behind the screen. The three chlorine atoms form a triangle around the aluminum. My aluminum orbitals look like this. You can see that I've got most of my electron density projecting towards the chlorines because I'm trying to get maximum overlap with those chlorine orbitals. That's where my electron pairs are going to mostly find themselves. I still have a small residual electron probability behind the aluminum on those bonds, but I mostly expect to find my bonds, my electrons directly between the aluminum and chlorine, and have an angle of 120 degrees. Well, if we go back and look at the distribution of our electrons, we see that we still have a p orbital available. That p orbital doesn't have any electrons in it, but that p orbital is physically still there. It's above and below the plane of my triangle. Because there are no electrons in it currently, there's no repulsion, but the orbital is still there. And it turns out, if we look at the reactivity of aluminum chloride, its reactivity is determined by that empty p orbital. If it's going to react with something, it's going to react with a molecule that has an extra electron pair that it can insert in that empty orbital. Well, how about a simple organic molecule like formaldehyde? Well, carbon is our central atom in formaldehyde. If we were going to draw a Lewis structure, it would look like this, keeping in mind that Lewis structures are not real, but they're a great way to keep track, to do the bookkeeping on electrons. Well, carbon starts out with 4 electrons. 4 electrons means that I have to account for 3 electrons in single bonds, sp2. That sp2 hybridization tells me that the molecule is trigonal planar. Well, why is it sp2 and not sp3? Well, I can only have 2 electrons being shared between the carbon and oxygen directly geometrically between the 2 nuclei. If I'm going to share more than 2 electrons with that oxygen, I need to leave one of my electrons from the carbon unhybridized in the p orbital so that I can get side-by-side overlap for a pi bond. So a carbon-oxygen double bond, that first bond is head-to-head overlap, but directly geometrically between the nuclei. That's my sp2 hybridization. But the second bond formed between the carbon and oxygen now has to be out of that plane and has to be side-to-side overlap with that between the carbon unhybridized p orbital on oxygen unhybridized p orbital, so that I can get that side-to-side overlap. So the first bond that we form between carbon and oxygen, which is located where the electrons are located directly between the 2 nuclei, is my sigma bond. The second bond formed above and below the first bond with that side-to-side overlap is my pi bond. And because it does not have the same level of overlap, it doesn't have the same energy, and as a result, it's a lower energy bond, even though the double bond overall, when I add my sigma and pi bonds together, are a stronger bond.